Hello, welcome to my presentation on LabVIEW programming patterns and frameworks. My name is Darren Nadinger. I'm a CLA, and I'm currently a principal TSC at NI. Before I get started on the content of the presentation, I'd like to mention that this presentation is part of a series that I'm giving on LabVIEW troubleshooting. If you'd like to see the slides and videos for that series, please check out the bit.ly link shown in the slide, bit.ly/dnatlv troubleshooting. There you will find links to all of the video recordings for the presentations in the series, along with downloads for the slides and the demos. The slides are particularly important because in these slides, I have a lot of links to additional resources, and you're going to want to download the slides to gain access to those links. Now that we've got that out of the way, I'd like to get into the content for the presentation. First, I'm going to be introducing LabVIEW design patterns and frameworks, and I'd like to thank Andreas K. Because a lot of the content in this section of the presentation was borrowed from a design patterns presentation that he gave. So you may be wondering, I'm giving a presentation on LabVIEW troubleshooting. Why am I talking about design patterns and frameworks? What does that have to do with troubleshooting LabVIEW applications? Well, a lot of the time for LabVIEW programmers, you're going to be looking at LabVIEW code that has been written by other developers. And it's helpful, it actually speeds up the troubleshooting process if when you open the code, you're immediately familiar with whatever pattern or framework was used when you open that code. It's helpful to open a project and within seeing just the classes and libraries or maybe one block diagram to know, oh, this was written with active frameworks. So I can make a lot of assumptions about what I'm seeing here. It's also helpful when you open the diagrams and the project and you say, whoa, it's very clear that no one or whoever wrote this code was not familiar with design patterns and frameworks because I'm not seeing any sort of patterns in this code. That can sort of help set expectations when you start troubleshooting issues. But if you open up a project and you can observe that it was written with active framework or DQMH or the NIQ message handler or any number of established frameworks or patterns, you can make some basic assumptions from the start. You know that some of the fundamentals of how the code works are going to be baked into the framework that was used. For example, the starting of different code modules, how they stop, how they communicate between them, when they show their front panels, hide their front panels, when they report errors, you know that those things are probably taken care of pretty well by the framework that was used. And you also know that if there's a problem in the code, like zombie VIs are left running after the application is done, or errors are not being reported properly, that's likely the fault of the developer who wrote the application and not the fault of the framework itself. Since again, those types of things are usually handled by the framework. So, and keep in mind that if a framework wasn't used, if the code was just thrown together from blank VIs, then all bets are off in terms of, are there going to be race conditions? Are VIs going to shut down properly? Are modules communicating properly to one another? The answer to a lot of those questions might be no, because a framework was not used at the start of development. So I'm using these terms, design pattern, framework. Let's do a bit of a glossary here. When I say design pattern, what exactly am I referring to? I'm referring to a general reusable solution to a common problem that can happen in software. And why should you use a design pattern? And the reason is that these are patterns that have been established by many developers before you. They've been defined, they've been refined. And you won't have to reinvent the wheel when it comes to accomplishing common tasks if you start off with a design pattern. Now, if you come from other programming environments besides LabVIEW, as soon as I say the term design pattern, you might be thinking of the book called the Gang of Four Design Patterns book. I've got a picture of its cover here on the slide. This is the most well-known resource for design pattern information in regards to general software development. This book was not written with a particular language in mind. However, there are some peculiarities about programming in LabVIEW that may not necessarily be covered in the official design patterns book. And so we have a useful resource. Sam Taggart over at SAS Workshops has a blog post about how the Gang of Four design patterns book relates to design patterns in LabVIEW. So again, I recommend at the beginning, I recommend again now, download the slides from this presentation so that you have access to all the links like the one on this slide for Sam's blog post. So the most common design pattern in LabVIEW, hopefully you've heard of it before, hopefully you've seen it, is the state machine. If you see a while loop with a case structure inside of it, and that case structure has an enum or a string wired to its selector, this is probably a state machine that you're dealing with. And a state machine allows you to simply execute a sequence of events in a defined order. Now, you may be thinking that's also what a flat sequence structure can do, and you're right. But the thing about a state machine is that the order is determined programmatically. With a flat sequence structure, the order is determined statically. And so whatever is in those frames is going to continue executing in that exact order, unless you click the abort button on the VI, which you should never click the abort button on a VI. With a state machine, you're defining that order programmatically. So some of the states could be skipped. Some of them could be executed multiple times in a row. That's all up to the discretion of how the state machine was written in the first place. Now, a type of state machine is an event-based state machine. And this is typically a user interface of some kind where one of the states in the state machine has an event structure that's waiting for things to happen on the front panel. This pattern is actually available as a project template in LabVIEW. If you go into the Create Project dialog, you can pick the simple state machine out of the list, and it will generate a project for you containing an event-based state machine, just like the one shown on the slide here. Now, another design pattern, probably the second most common that you'll see after a state machine, is the one that's called a producer-consumer. Producer-consumer is referring to a multi-loop design on a block diagram, where one loop, in its purest form, one loop will generate data, it produces information, and then another loop consumes that same information. And that's where we get the name producer-consumer. And the way that the data is transferred between the two loops is usually with a queue. Now, the thing about a queue is that, if you send information into the queue faster than you pull information out, your queue is going to grow in size, unless you set a maximum size on it. And once you do that, now you have to be concerned about the code that wants to in-queue into the queue. It can't do it while the queue is full. So one of the things that you have to keep in mind when using the producer-consumer pattern is you want to make sure that the rate of consumption equals or is greater to the rate of production. Now, if you want to see what that looks like, here is an example of what the producer-consumer pattern will look like on a block diagram. So you can see the two loops that I talked about before. Outside of the loops, we create and destroy a queue. Within the loops, you can see inside the producer loop, we are in-queuing data into the queue. In the consumer loop, we are dequeuing data from the queue. So this is the most common instantiation you'll see of producer-consumer. Now, those are just examples of design patterns. There's a few others, but state machine and producer-consumer are probably the most common. Now, what about a framework? So I'm differentiating those terms. Design pattern, what I just described, those patterns like state machine and producer-consumer. What is a framework? Well, a framework, I want to say, is a starting point for an application. If you're about to start an application, it's probably a little bit simplistic to say, I'm going to start this application with a producer-consumer. That's a pattern that you might use in the application, but I wouldn't say producer-consumer counts as a starting point for an application. Same with the state machine. But with a framework, you've got a starting point for an application that is usually based on design patterns. If you dig down into Active Framework at its lowest level, it really is a producer-consumer with a queue. I mean, there's a whole lot of other stuff sitting on top of it, but ultimately, Active Framework is built upon producer-consumer patterns. So is the Delacorte queued message handler. But the thing about a framework is that you've got a whole lot of stuff sitting on top of this pattern that usually includes tooling to help the developer who's writing the application. For example, in Active Framework, there are right-click menus in the project window that let you create messages to communicate between your actors. So whenever you need a new message to communicate from one actor to another, you don't start from scratch with a blank VI and start writing that code. You've got tools built into Active Framework that can create those for you. Another reason why using frameworks is so powerful, it's a time saver, and it prevents a lot of bugs that might happen if you're trying to write some of that code from scratch. And that's why you should use that. I mean, mainly if you ask someone like Fabiola de la Cueva, who is the lead architect on the Delacorte Qt message handler, she would probably tell you that the DQMH, the actual design of the framework, isn't all that special. She would probably tell you that the main reason people like to use DQMH is because of the tooling that makes it so easy to construct the communication between modules and to create new modules and things like that. So popular frameworks, I've mentioned AF, I've mentioned DQMH, but here's a list of several that I, from experience, have seen LabVIEW programmers use for their applications. The NI-Qt message handler ships with LabVIEW, and so does the actor framework. And both of those you can create from the Create Project dialog in LabVIEW. But there's also several third-party frameworks, frameworks not written by NI, that are popular as well. The DQMH I've described already, but there's also JKI state machine objects, the messenger library, TLB prime. Those are all frameworks that I have seen used successfully in applications as well. So I'm going to switch over to LabVIEW here and just demo a few things related to developing with frameworks. So the first thing I'm going to do is I'm going to launch the Create Project window. So if you go to File, Create Project, that's the same as clicking on the Create Project button on the Getting Started window. This is basically where you can see a lot of starting points for applications. Obviously, blank project and blank VI aren't the greatest starting points, even though they're at the top of the list. But as you look through the other parts of the list, you can see things like the Delacorte QMH. And when you click on more information, you can see basically the help topic to help you get started using DQMH. Similarly, if we go into the Create Project dialog and click on the more information link for Actor Framework, we can also see the getting started information for Actor Framework. And these, if you have never used these frameworks before, you definitely want to read these help documents. Now, if we go into, I've already opened up a DQMH project. This is actually the shipping example for DQMH. I am not going to teach DQMH in this presentation. I'm just trying to sort of introduce why using these frameworks can be helpful for not only application development, but troubleshooting as well. So the thing about DQMH is it is very recognizable. If you've just studied a little bit about DQMH, you can look at a diagram like this one right here and instantly know that you're working with DQMH. It's got a similar pattern to the NI-QMH, but right away you see things like the DQMH in QVIs. You see things like the event structure and the message case structure. You see things like the DQMH module admin class being passed around. These are all things that when I open the block diagram, I know, okay, I'm dealing with a DQMH application. I can make a lot of assumptions before I start going into troubleshooting. Similarly, one of the great things about DQMH is that it provides testers, testers that are created for you that you maintain as you write your application. And the testers are also very recognizable as well. So I see a diagram that looks like this with a VI that's registering for broadcast or DQMH. Again, I don't expect you to know what these terms are if you haven't used it, but the point is that you do want to become familiar with these frameworks so that as you're troubleshooting applications, you can come in, make some assumptions. Right away, I see that this is a tester. It looks like it's been relatively well maintained because I see buttons for activating the request for this module. I see definitely they're handling the broadcast for this module. So right away, this tells me that whoever wrote this code was familiar with DQMH and is keeping their tester maintained. So that should help me a lot when I'm trying to troubleshoot the application. That's another great thing about DQMH specifically, I'll just mention quickly, is that when you're working with DQMH, the tester for your module, if you keep it up to date, then when you're having problems with your main application, if you get those problems narrowed down to a particular module, you don't have to run your main application and debug from there. You can run just that module from its tester and be able to debug that way. So just an example of as you become familiar with these types of frameworks, the types of things that are going to be a lot easier to learn and a lot easier to troubleshoot when you know how things work. All right, so I'm going to head back over to the slides now and just briefly talk about design pattern misuse. So again, this is a troubleshooting presentation. I'm trying to give advice on how to troubleshoot LabVIEW apps. And if you have an application that's having trouble and you open up the block diagram and you see multiple state machine patterns sitting on the same block diagram running in parallel, that might be a bad sign. The state machine pattern is not designed for parallel loop execution. You can do it. I mean, there's nothing stopping you from making a copy of a state machine on the block diagram and having two state loops with two case structures and two event structures. Goodness, I hope you didn't do that. But there's nothing stopping you from doing that. But when there are problems with the code and you open the block diagram, that is definitely a misuse of the pattern. A few other things to look out for I've listed on the slide here, just things that I've encountered along the way as a LabVIEW developer. The NIQMH is designed for parallel loop execution. The producer consumer by definition is a pattern that uses multiple loops. However, the NIQMH is not really designed for instantiating dynamic loop execution. So, as your code is running, your code programmatically wants to spawn a new instance of a parallel loop running. The NIQMH is not designed for that. If you try and shoehorn that behavior into the NIQMH, you're going to have problems. Now, DQMH and Actor Framework, those frameworks are designed for dynamic instantiation of parallel actors. So if that's something that you need, that you would probably want to use one of those frameworks. Another misuse that I've seen in DQMH is trying to take a DQMH module and make it act like a state machine by cramming a bunch of state machine behavior into the loop that's only supposed to be handling messages for that module. It'll work, but now you've got one message handling loop that's also trying to maintain state. So it's handling messages coming in from other modules, but also executing some sort of state machine-like behavior. That is a bad sign probably for issues that you might have to troubleshoot in the future. DQMH has the concept of helper loops. If you need to maintain state in your module, you want to use a helper loop. Again, the kind of thing you'll learn as you start to become more familiar with these frameworks. And then just a general rule, if you've got a single module in, whether it's Actor Framework, DQMH, NIQMH, any of the other popular frameworks, doesn't really matter. If you've got one module that's trying to do a whole bunch of stuff, if you notice that the same loop that is doing your error logging is also doing your data logging, that's probably not a good sign. That's probably a sign that you need to have an error logging module and a data logging module and have those be separate actors in your application. So another thing to look out for when troubleshooting applications, is there a design diagram of the application? Design diagrams, if you're doing class-based development, you'll often be using something called a UML diagram. If that sounds scary or if that's nothing you've ever heard before, don't worry about it. Take a look at the diagram that's on the slide here. I made that in PowerPoint, so I didn't need any sort of special editor. This is a diagram for a project that ships with LabVIEW, actually. In the Create Project dialog, if you create a continuous measurement and logging sample project, this diagram illustrates the design of that project. So, it doesn't have to be a formal diagram of some sort. If you're worried that you have to make a UML diagram of every project, no, you don't have to do that. You could take your whiteboard, if you've got one at home, and draw out a diagram on there and take a picture of it. That's good enough. There needs to be something to communicate to people who are developing or troubleshooting the application what the design of that application is. And so providing that kind of design diagram is very important, no matter what the form factor is. Thankfully, there is an excellent tool that helps with generating this documentation. And this is a relatively new tool. I'm giving this presentation in January 2021. AntiDoc's only been out for a few months now. And it is an excellent tool for documenting projects, whether they are DQMH projects or other projects developed with other frameworks. AntiDoc will automatically generate not only documentation like on the actual VIs within your libraries, but also the relationships between those VIs and libraries themselves. I've just pasted a couple of example diagrams here into the slide of some diagrams that were automatically generated by AntiDoc. I didn't have to do anything other than point AntiDoc at my project and say, go. And AntiDoc went and generated lots of documentation, including these diagrams that represent the relationship between VIs and each other and other libraries in my project. So definitely check out AntiDoc if you haven't already. So if you are getting started with frameworks, I recommend downloading these slides and taking a look at all of the links in the slides. The reason I have Active Framework and DQMH bolded is because just from my experience, those are the two most popular LabVIEW frameworks out there. But as I mentioned, the others are used quite a bit as well. And each one of them has a resource for getting started with that framework, learning details about it, shipping examples, project templates, things of that nature. So definitely download these slides, get those links, and start learning about all those frameworks. If I were starting from scratch and knew very little about any of these, I would start by learning DQMH and Active Framework, just because chances are if you're troubleshooting code that you didn't write and it was written with a framework, it was probably written with one of those. All right, so I'm going to move on to the next part of the presentation. Best practices for error generation and propagation. These slides were taken from another more extensive presentation on what we would call error handling, which I'll get into here in a minute. It's a presentation I've given before, bit.ly/dnat errors to download that whole presentation. I will just go over some highlights from that presentation here now, as they relate to troubleshooting LabVIEW applications. So in this section, I'm going to talk about error handling, but the problem is that the term error handling is kind of overloaded and overused. In my preference, I would prefer we stop using the term error handling, because it can mean any one of the 5 things shown on this slide here. Error generation, which is the creation of an error value on a block diagram. Error propagation, which is propagating an error value through a block diagram. Error response, which is what do you do when an error happens? Do you retry something? Do you clear the error because you don't care about it? Do you change it to another error value? Those are all things you can do to respond to an error value. Error display, which is, how do you let the end user of the application know that something went wrong? And then error logging, which is the behind the scenes, we are going to keep track of all the things that went wrong by logging. When someone says error handling, they could be referring to any one or more of these 5 things that are shown on the slide here. So I prefer we use the specific terms described in this slide when talking about working with errors. And in this section of the presentation, I'm mainly going to be talking about error generation and error propagation as they relate to troubleshooting LabVIEW applications. So as I mentioned before, error generation is the creation of an error value whenever something goes wrong in your LabVIEW code. And there are only 2 ways that error values are generated in LabVIEW. One of those is with built-in nodes. So if you've got a open create replace file function and you pass it a path to, you pass it a relative path, something that can't be written to, that function is going to return an error on its error output. Similarly, if you're calling DLLs with call library nodes and you do something wrong in the way you've set up the parameters of the DLL call, then or if you pass in values that don't make sense once they get to the DLL, it might return a value that corresponds to some sort of error. The other way besides built-in nodes is to actually write LabVIEW code that generates an error value. For example, you may be doing some math on a block diagram, and if you find a value that went out of range, you're using the numeric functions, right? Add, subtract, multiply. Those don't have error terminals. But you as a programmer have decided, oh, we've gotten into a case where our value's out of range. I need to return an error. You might have LabVIEW code in a case structure that says, all right, return this error cluster. And you might be generating that with an error ring, like shown on the slide. If you have a numeric error code that you want to convert to an error cluster, you might use error cluster from error code, like shown on the slide. What you don't want to do is the picture in the bottom right, where you are building the error cluster yourself. I see this all over the place in user code. Sadly, I see it in iCode sometimes. You don't want to use the bundle by name or the bundle function to build the error cluster yourself. You want to use one of the other 2 methods shown in the slide, the error cluster from error code VI or the error ring. If you do it with the approach with the bundle by name, you're going to have a few problems. One, your error cluster is not going to have call chain information, which is really useful when troubleshooting things. 2, if you have a hard-coded VI name there and you go rename the VI but forget to change the constant there, now you've got an error code that's referring to a VI that may not exist or a VI that isn't this current VI. So now that's going to be difficult when you're troubleshooting. Don't build the error cluster yourself. Always use error ring or error cluster from error code. That's definitely going to help when you're actually having to troubleshoot that error value that got generated on a block diagram. So that was error generation. Now what about error propagation? Error propagation is when you have an error value in your LabVIEW code and it needs to propagate through your LabVIEW code. Now, sometimes there's a lot of aspects to how to propagate error values. You might be taking an error cluster and forking it into parallel code paths. Later on, you might be merging those parallel code paths, the errors from those parallel code paths. Sometimes you'll have a case structure around some code that you don't want to execute when an error occurs. And when you're writing that propagation code, you might be using merge errors or case structures or shift registers. But if there's one thing I want you to remember about error propagation, it is this: don't break the error chain. If you think about any sub-VI or any function on a LabVIEW block diagram that has an error input and an error output, like all of the VIs in function that you see on this diagram, that sub-VI, it has faith in a higher power. And that higher power is you, the LabVIEW programmer. That sub-VI has faith that if it returns an error, you, the programmer, are going to make sure that that error reaches its final resting place. What that final resting place is, it could be a general error handler, it could be some error logging scheme. That sub-VI doesn't really care. It just cares that you, as the LabVIEW programmer, are shepherding that error to its final place. All it takes is a single place in a massive VI hierarchy that breaks the error chain to cause any upstream error generated to be lost forever downstream. And those type of breakages in the error propagation can cause hours-long debugging sessions where something has gone wrong in your code, but you have no idea what it is because you didn't get the error that was generated. There are several ways you can break the error chain in your LabVIEW code, and thankfully, several tools that can help you find when it happens. First, let's talk about how the error chain can be broken. The first way is the most obvious way, which is what I just talked about. You have an error output from something and you just don't propagate it through. You can see that in the top picture there, if the DACMX read returns an error and the loop stops, whoever wrote this code forgot to wire that error out of the loop. And so that whatever caused the DACMX read to error out, we're not going to find out about because somebody forgot to wire that error terminal. Another extremely common way that I see people break the error chain is with zero iteration for loops. If you take a look at that block diagram, the second block diagram on the slide, you'll see that the error tunnels are not shift registers. And I'm going to talk about that more in a demo that I'm about to give. But that code, if that for loop iterates 0 times and there was an upstream error, we would never find out about it. And in the bottom picture, a bit more of an esoteric issue, but still one that I want to mention because I see it happen a lot in code. We want to always make sure that the first error that occurred as your code was executing is the one that gets reported. Even if multiple errors happen, you generally want to find out about the first one because the first one probably caused some of the later ones to happen. So you always want to find out about the first error. But if you look at that bottom picture in the slide, you can see that the merge errors function does not have the incoming error to this VI as its top input. So what that means is if that sub VI in the upper left corner of that block diagram generates an error, that error is going to be prioritized over the incoming error to this sub VI. That is not what you want to do. That is sloppy merge errors ordering. Always propagate the incoming error to a VI as the first error on the merge errors function. So I mentioned I was going to do a demo about zero iteration for loops. Let's switch over to that now. All right, so I'm going to write a simple VI that writes data to a TDMS file. So I'm going to do open TDMS. And then in a loop, I'm going to do TDMS write. And then after the loop's done, I'm going to do TDMS close. And I'm going to use Control-Space-Control-W, the quick drop shortcut to automatically wire nodes. If you didn't know about that, pretty handy. And then let's see, I'm going to write to ctemp blah.tdms. And what do I want to write to it? How about an array of numeric values? And we'll write to it one row at a time. So very simple code here. And now when I create an error indicator and run the code, I get an error. So let's use explain error to see what the problem is. It says invalid TDMS file reference. Now, I happen to know, because I wrote this demo, that that is a very misleading error. That is not what the problem is. The problem is that we've specified a file path to a TDMS file that doesn't exist. But watch what happens when I run this code in execution highlighting mode. Watch in particular what comes out of this function right here. You can see we have an error 7 come out of this function, but that is not the error that was returned. Now I'm going to run the code again with execution highlighting, but now watch the error output from this tunnel on the for loop right here. We can see that that tunnel returned no error. And the reason it returned no error is because this for loop ran 0 times. In case you didn't know, this is an extremely important detail about LabVIEW. When you have a for loop that runs 0 times, all tunnels return the default value for that data type when the for loop runs 0 times. So that means this top tunnel here is going to return an invalid reference. And this bottom tunnel here is going to return the default value for an error cluster, which is no error, error code 0. You have to make sure you keep an eye out for this on your block diagram. There's a very easy way to avoid this problem, which is replace those tunnels with shift registers. And this is just how LabVIEW works. If a for loop runs 0 times, all shift registers will return the value that was passed in to the left side of the shift register. So whatever reference you wired in here is going to come out over here when this loop runs 0 times. Whatever error you wired in here is going to come out here when this for loop runs 0 times. Now, if we run the code again with execution highlighting turned on, we'll see that that error 7 made its way out over here. And now the error 7 was reported. And we can now see, oh, this code is erroring out, not because of an invalid reference, which is what it told us originally, but because the file wasn't found, which is a much more helpful error. Now, let's talk about just different decisions you might make as a LabVIEW programmer. What if you wanted this? So this is how this code works right now. We are now passing through values if the for loop runs 0 times, but now we've got another problem. If this function, the TDMS write, ever returns an error, and we're passing that into a shift register, that means all future runs of this function in future iterations of the for loop will have that error coming in. Well, maybe we don't want that. Maybe we want the TDMS write to write no matter what, even if an error was generated on the previous iteration. Okay, well, that's definitely possible. Let's go switch back to tunnels. So now we're going to have the same problem we had before if this code runs 0 times. So now one possibility is that we can build up the errors on the tunnel, and now we can just merge them after the for loop runs. This would work. One thing we might want to watch out for is if this array has millions of rows, then we're going to have millions of error clusters built up on this border. Typically not a concern, but definitely a concern if you know for a fact this code's going to run a bunch of times. But there's still another problem with this error propagation. And it's the same problem we had before. If this for loop runs 0 times, then this function, which returns an error, that error is going to be lost here. So if you really want this code to propagate errors properly, you're going to need to do something like this, where you not only merge the errors coming in from this function, but also the previous error, and make sure that it's the top input. Because if you do this, then now you're running into the sloppy merge errors ordering we talked about before, where one of these errors, if this runs more than 0 times, is going to take precedence over this error. So make sure that you always watch out for error ordering, watch out for 0 iteration for loops. Now, one other thing I want to mention is some peculiarities having to do with parallel for loops. So I'm going to change this for loop to be parallel. All right, so this is now a parallel for loop. You can see that my code is broken. The reason that it's broken is because we can't have these shift registers on this guy. So I'm going to replace these shift registers with tunnels. So our code's not broken, but again, it's going to have the same 0 iteration concerns that we had before. So one way I'm going to get around that is I'm going to pass my reference around here because that doesn't need to be passed through. And then another thing I'm going to do is a relatively new feature to LabVIEW. I'm going to, and that shift register, that is a new feature. I think it was introduced in LabVIEW 2018 or 2019 called error. This is a feature specific to parallel for loops. And it basically allows you to pass an error value through the for loop as if you had a shift register on it. So this code that you see here is pretty much the same as if we did this. The previous approach that we saw before. Only, as you saw, the error register looks a lot nicer. So if you're in a relatively recent version of LabVIEW, passing errors through parallel for loops is more manageable with the use of the error registers than it was in previous LabVIEW versions. So I mentioned before that we have some tools that allow us to avoid breaking the error chain in our LabVIEW code. Most of those tools are in the VI Analyzer toolkit. So the error cluster wired test detects those situations that I talked about before, where you've got a sub-VI or a function with an error output that's unwired. And this test has some options that allow you to ignore certain objects that you frequently don't wire the error output for. We've also got the unused code test. Now, this is going to detect issues like that DAC-MX code I showed before, where somebody wired to the border of the while loop, but forgot to wire that error cluster onto the future code. The unused code test will detect that. Then we've also got the for loop error handling test that pretty much detects all of the issues that I just showed in my demo, where you've got a for loop that could run 0 times or you're merging errors incorrectly. And that test is available in 2018 or later. So several tests available in the VI Analyzer toolkit to find some of these error generation and propagation issues. And finally, I'm just going to mention auto error handling. I do not use auto error handling. I do not like the feature. Some developers do use it and they like it because it does help them find some of these error conditions. The thing about auto error handling that you have to watch out for is that there's no easy way in LabVIEW to turn it on or off on an entire code base. So you'll probably need to write some tooling if that is important to you to have that feature. It's turned on per VI in your code. So if you want to turn it on for everything and then turn it off for everything as part of a debugging procedure, you're going to need to write some tooling for that. So just to summarize all of the error stuff I've been talking about, you want to make a conscious decision about every error wire that you create or choose not to create in your block diagram. This is going to help down the line when you're having to troubleshoot error conditions. When you open a block diagram, you should know exactly how that diagram functions with an error condition if that code has been written with the patterns described in this presentation and with good documentation. Auto error handling can be used to find some of these error generation and propagation issues, but unfortunately, there's not an easy way to know when it's been turned on versus when it has been turned off. There's no visual indication of that. So that's something to watch out for if you're using auto error handling. But ultimately, to make it easier to troubleshoot your LabVIEW code, the error chain should be immediately obvious on every block diagram that you write or that you look at. All right, so for the final section of the presentation, I'm going to talk about code smells. Thanks to Mark Ridgely, who originally wrote a code smells presentation. I've got the link for it here in the slide. I'm borrowing a lot of his content for this part of this slide. So thank you, Mark, for that. What's a code smell? Have you ever heard that term before? It's a term that I see LabVIEW programmers use quite a bit. A code smell is not a bug. Like it's your code isn't functioning incorrectly, but it's when you look at the code and you see this is a pattern or this is a choice that I think could possibly cause problems down the road. And here's some common code smells that you're going to see. I've got some demos for most of these as we move on in the slides, so I'm not going to go through each one here, but there are several things that experienced LabVIEW programmers, when they look at code and they say, that's a code smell right there, they're probably referring to one of these things here in the slide, and possibly some others as well. The thing about code smells is that an experienced LabVIEW programmer is going to have a hard time ignoring them, because he knows that it is very likely going to be something that causes a bug that he has to troubleshoot down the road. And I'm mainly focusing on LabVIEW code smells here, but any part of your software, teststand, .NET, in any part of your software could have some code smells in it. So here's the thing. When you see a code smell, and again, I'm going to demo some here in a minute, don't look the other way. You want to refactor that code. I've been in the technical support group at NI for most of 2020, and I've seen a lot of customer code, and I gave the recommendation to refactor that code several times, and you kind of don't want to look the other way. You want to say, this is going, I'm troubleshooting an issue right now. This may not be exactly related to the issue I'm troubleshooting now, but this is a code smell that is almost assuredly going to cause a problem down the road. So when you tell somebody to refactor, what does that mean? Refactoring almost never means adding features to code, and refactoring almost never means fixing bugs in code. Refactoring is basically a redesign. So the code is going to do the same thing that it did before, but the code is now more readable and maintainable. And hopefully that means that even though you didn't add any features and even though you didn't fix any bugs, you're saving yourself time and money down the line on future bugs that you're hopefully avoiding with the refactor. Unfortunately, that refactoring isn't a terribly attractive task to convince a manager that needs to be done, or to convince a client or whoever. They've identified a small bug or a small feature that needs to be added, and when you say, well, I can technically get that added or fixed, in a matter of hours, but I'm noticing that this code really needs a refactor, and that's going to take days or weeks. It's really hard to convince, managers, clients, et cetera, that time is worth the investment when you're comparing, when you're just looking at the here and now, when you're just looking at the, oh, well, just spend a couple hours and fix the bug and it'll be working, versus spend a week and the code's still working the same way that it does now. This is an investment in the future. Hopefully, if you're listening to me say this, you're in complete agreement with me here. I'm not having to convince you of anything, but it's something that definitely comes up. When you're troubleshooting an app, you might find the cause relatively quickly, but you also might identify enough code smells that you feel like recommending a refactor is an important part of the process. So several things that might be code smells that you may want to consider for refactoring. Well, the first is poor variable naming. And again, these are the kind of code smells that can happen in LabVIEW code or somewhere else. What you're looking at here, I believe, is test stand. It's not even LabVIEW. And on the left, we have excessively short names for variables. As a LabVIEW programmer, if I saw a bunch of locals, or if I saw a formula node with these names in them, like iCount, isFF, mloop, et cetera, the ones in the left picture, it would be difficult for me to figure out what was going on purely by looking at the variable names. Then over on the right, we have excessively long names. Every single variable has that prefix on it. So now we've got a bunch of noise as we're trying to browse a list of variables. If this were in LabVIEW code and these were local or global variables, now I've got a bunch of horizontal space being taken up on my block diagram that probably isn't necessary. The LabVIEW style checklist is available on ni.com. It contains pages and pages and pages of recommendations for good LabVIEW style, including some guidelines regarding naming of things. So it's a good resource for that. Another code smell is duplicated code. So look at this block diagram right here. The contents, or I guess basically the whole right half of the block diagram has been duplicated 3 times. And then if you look in the upper left of the case structure, you'll see some logic has been duplicated 3 times with the add one and subtract one. These are the kinds of things that make the most sense to implement in a single sub-VI, and then call that sub-VI 3 times. When you've got duplicated code like this, what can very often happen is there will be a bug in the code, or you'll do some sort of improvement to it, And if you're looking at just this block diagram, it's pretty obvious that you've got 3 copies of each thing, so make sure to make that change. But once you've copied code across multiple VIs, or even through multiple cases of the same VI, you're going to forget to make those changes. And that is often something that needs to be troubleshot. Somebody makes a change to the code, thinks it fixes a bug, but then doesn't realize that same change has to be made somewhere else because of duplicated code. So watch out for that. Definitely a code smell. Another thing to consider refactoring is unnecessary complexity. And this is a hard one because a lot of the times the code that is unnecessarily complex takes a while to sort of parse and figure out what it's doing. Let's look at this while loop here. What in the world is this doing? So it looks like it's taking the current VI's path, turning it into a string, and then over multiple iterations, searching for a file path separator, which right there is a code smell to me, because if this code is working on Windows and I take it over to Linux, it is going to break because that path separator is going to be different. But anyway, so it is taking the path separator and rebuilding the path string from what I can tell. We're just taking what's before and what's after and putting a path separator. But on the very last iteration where we don't find a path separator, we're stopping the loop. So in case you haven't figured it out already, don't feel bad because I still hadn't figured it out by this point. That while loop is performing a strip path. That is all it's doing. It is taking the path and taking off the last piece of the path. This code is unnecessarily complex. All of that could be replaced with a strip path function. Keep an eye out for unnecessary complexity. I tend to notice it when it's smaller scale than this. Like this while loop took me 45 seconds to a minute to finally figure out, oh, that's just doing a strip path. I tend to keep an eye out for unnecessarily complex implementations of things, but usually a lot simpler than this. Try to train yourself to look for those patterns on diagrams because, again, somebody spent the time to re-implement strip path and may have made a mistake in that implementation. I don't think there's one here, but there might be. That's not something I need to think about when troubleshooting when I see a strip path function on a block diagram. So refactoring unnecessary complexity, definitely a good task to do when you see that code smell. Here's another pattern that I unfortunately see in a lot of customer code. They take a VI that does something, and then they realize that they need it to do something else, but they don't want to break existing code that calls that VI. So they'll save a copy of it with the change and keep around the old VI. This is terrible to try to troubleshoot when problems happen because you have to see if something was changed, from a previous version. You don't even, when you see this, when there's a problem with the RS-232 read-write, and you look in the file structure for this code and you see 20 VIs that say RS-232 read-write, you start to wonder, well, are they using the right one? Should they be using another one? Then you start looking through all these VIs and realize that there's just little changes in between them. Definitely a problem. If I were refactoring this code, there would be a single RS-232 read-write probably, maybe 1 or 2, but definitely not 20 or so like there are in this slide. Now, refactoring spaghetti code is probably one of the hardest things to do because it's really hard to figure out where to start. In this example, you can even see with the nav window that the diagram that you see is only about 1/3 of the entire size of the diagram. So there are times in refactoring where it makes sense to throw things away and start over. And to be honest, I would probably throw this code away and start over if I was refactoring. But one thing you want to keep in mind, this is something that I've heard from Fabiola de la Cueva, who's the lead architect on DQMH. She says that when you're refactoring spaghetti code, it's okay to throw out the spaghetti code, but take a look and see if you can find any tasty meatballs first. And by that, she means reusable pieces of code. We can see in this spaghetti diagram here, it does look terrible, but I also see 3 sub-VIs there. So there's a chance that there's some code in those sub-VIs or the sub-VIs themselves that I could reuse when I'm doing a refactor. So I'm not starting completely from scratch. I've just thrown away the spaghetti and kept some of the useful meatballs before I did. This diagram looks very similar to what I see from developers who have experience with text-based programming and no LabVIEW training. This is the type of diagram written by someone who assumes everything is a variable. This is the type of diagram written by someone who does not understand data flow in LabVIEW. Whenever you discover code that looks like this, it's probably worth a refactor. We could probably get rid of almost all of those globals, or at the very least, get rid of having to read and write them on the same block diagram and replace that with just using a wire. I see this kind of code too. This is also something that can be difficult to refactor because it may seem like, well, I could use any or all of those outputs from that sub VI, so they all need to be there just in case. This is the type of refactor that I think makes the most sense to do with LabVIEW classes, because if we were to replace that, what I assume the IP is a cluster or something along those lines, if we're not passing a class between the VIs and our API, we can now add a property-based API to our class where the class itself stores whatever information is needed for the device or whatever we're working with. And if you need to access any of that, you can use a property node. And that way you can just pull out the single item that you need as opposed to having these VIs with a million parameters on their contain. There's a lot of different ways to potentially solve this issue, but I think properties with classes is one of the best ways. So for my final demo here, I'm going to talk about cyclomatic complexity. Now, if you've never heard that term before, cyclomatic complexity basically means the amount of possible code paths within your diagram. So if you've got a case structure with 2 frames, that would be a cyclomatic complexity of 2. If you've got a case structure with 10 frames, that would be a complexity of 10. Basically, how many possible avenues can this code execute through? And cyclomatic complexity can sometimes be a code smell. If your code has so many different possible paths, it's going to be difficult to test. And when you're troubleshooting, there's so many different code paths that could happen in that VI. That could be a cause for concern when you're trying to debug or troubleshoot the application. So going back into LabVIEW, I am going to show a tool in the VI analyzer. It is the cyclomatic complexity test. And I'm going to analyze 2 VIs that are just example VIs that ship with LabVIEW. One of them is this calculate normals VI, and the other one is one of our actor framework example VIs. And I'm just going to run our complexity metrics test. And we're going to see in the results that we had a couple of failures. First, let's look at actor core. If I show you this VI, this is a VI that's shown as a UI. As part of our example, it lets you add customers and cashiers and baristas to a coffee shop that's being simulated. If we look at the block diagram, this block diagram is relatively simple. This is and again, my familiarity with actor framework allows me to open this diagram and see, this is an actor core VI from actor framework. This is the standard design for it where the parent call is typically running in parallel with an event loop if this is a UI. So right away, I've got a head start because I'm familiar with this pattern. And remember, I mentioned the cyclomatic complexity test. This code failed that test. If we look, we can see that it has a cyclomatic complexity of 23, which means there are 23 independent paths that could execute on this block diagram. But the thing is, that's not really a problem because this is a UI, which means it's going to have an event structure, which means it's probably going to have an event frame for multiple things on the front panel. We've got these 9 buttons here. We might have events and this button here. We might have events for clicking in the list boxes. These are all relatively normal things. So this test failure, I would say, is probably not one we need to worry about. And thankfully, if we go back to the configuration of the VI analyzer, we can see that the cyclomatic complexity test has an option to ignore event structures, which is exactly what we want to do for a UI-based VI. So I'm going to go ahead and run the analysis again, and we will see that the actor core VI no longer shows up in our failures because we've said we don't need to worry about complexity introduced by event structure having multiple frames. But we still have this calculate normals VI that failed some tests. If we look and see what tests it failed, we can see one of the tests that failed was the modularity index test. This is a test that basically checks to see how modular the code is. How many sub-VIs do you have? In this case, it has a modularity index of 0, which means there are no sub-VIs. So without even looking at the block diagram, there's already a bit of a red flag here. And the other red flag is that this code failed the cyclomatic complexity test. We can see that this diagram is a cyclomatic complexity of 39. Well, let's look at it and see what it looks like. Now, this is a diagram that's going to concern me a little bit because we've got multiple frames of a case structure on the outside. And then within a given frame of the case structure, now we've got multiple frames inside of there. So this VI, if there is a bug in this VI, it is probably going to be difficult to debug because there is so much nesting and so many possible code paths. And remember what I mentioned before about duplicated code? Check out what this diagram looks like versus this diagram. I see one little difference right here, which is the math being done for the for loop. It looks to me like every single other thing on this block diagram is the same. If we go to another frame, we can see some similarities in this code as well between this diagram and this diagram. It looks like the only differences that I can spot offhand are these constant values and a constant value here, I guess. So once again, we've got some code that's been duplicated. And if we fix a bug on one of those frames, are we really going to remember to fix that same bug on another frame? It really seems like this code could be more modular. Things turned into sub-VIs where parameters are passed in. And when we've got sub-VIs in code, it's a lot easier to test in isolation when something goes wrong. That was my quick demo on cyclomatic complexity and how it can be sometimes used to help you identify issues on block diagrams. So a few tips on how to reduce complexity. Remove decision points when possible. For example, the error case structure surrounding a diagram content is almost never needed. I discussed this in more detail in the errors presentation that's linked in the slides. If you've got complex code like what we just saw, modularizing it makes it a lot easier to test in isolation because now you've got sub-VIs you can run on their own. Overuse of locals and globals can definitely cause race conditions, particularly when you write to those locals and globals in multiple places. And then one thing that experienced developers can help you with when troubleshooting applications, they are familiar with existing libraries. I see LabVIEW developers write their own libraries of things that have already been implemented elsewhere. And that's just another way to introduce problems in your code that you would have to troubleshoot. And when there is an existing library that accomplishes what you're trying to accomplish when rolling your own, those existing libraries, particularly for things that have been around forever, like OpenG is a good example. They've got recognized icons that everybody knows what the OpenG remove duplicates VI looks like, for example. I guess I shouldn't say everybody, but people who've been around for a while. There's corner cases and bugs that you're probably not going to identify when you make your first pass on rolling your own library that have already been found in the libraries that exist. So doing a code review with an experienced LabVIEW developer can very often help you identify places where you have tried to roll your own library where an existing would have worked just as well. So to summarize all of the slides that I've presented in the past hour, try to become familiar with popular LabVIEW frameworks like AF and DQMH and all the other ones that I talked about in these slides. So that when you open up a block diagram, when you're troubleshooting something, you know which framework it was written with, and you can make a lot of assumptions from there to save some time troubleshooting. There are some great tools out there to help you identify problems. I discussed in particular error propagation. There's some VI analyzer tests that can help you find those issues. And then code smells. The more you work with experienced developers, the more LabVIEW code you see, the more patterns you become familiar with, like what I described in these slides, the quicker you're going to be able to recognize those code smells and suggest refactoring. Refactoring is a hard sell a lot of the times. You have to focus on how much time it's going to save you troubleshooting in the long run by refactoring things now. So I've got some homework for you from this presentation. Thanks for sitting through for the hour. The first thing you want to do is download these slides at bit.ly/dnatlv troubleshooting. Next homework is in these slides, I have 6 links for those popular LabVIEW frameworks and getting started with them. Read the getting started materials for this so you are familiar with them and you know the basics about how they work for when you see that code out in the real world. I recommend starting with Active Framework and DQMH because those are the most popular, and then go from there when taking a look at the other ones. And finally, I had just a brief snippet from my what to expect when you're expecting an error presentation in these slides. I think you should watch the whole thing because my discussion about error propagation and error generation, I think is very important for developers to be able to write code that works with errors better and to know what to look for when troubleshooting code when errors occur as well. That's all I got for today. Thank you very much for watching this presentation.